Okay, so this quiz, just by looking at this first equation, what is the slope and what is the y-intercept? And which one is which? Okay, so the y-intercept is 3 and the slope is -2. Very good. What about the next one? Okay. So let me do this. I'm going to add 2y and add 6. I'm going to write it as 2y equals x plus 6. Is that okay? And then divide both sides by 2. Y equals 1/2 x plus 3. So what is the y-intercept? I don't think it's negative. It's 3, right? So y-intercept is still 3. And what is the slope? Half. Right? So the slope is a half, y-intercept is 3. So the next part, well, you had to sketch both of these lines. Before we sketch them, what do lines with the slope positive 1/2 and -2 will look like? What are they going to have? I mean, is there a special relationship between two lines with slopes -2 and positive 1/2? So they're reciprocals with a negative. So what is that going to give you? What kind of lines? Perpendicular. So before we even graph them, we're going to get perpendicular lines, right? We know that much. But anyway, so now if you sketch the graphs, so they both goes through 3, and one has a slope -2, so down 2/1. So here's that line, right? And the other one has a slope 1/2, so up 1/2. So to the best of your abilities, this is not really calibrated very well, so it's writing not where I want it to write. It's off by a few inches, but they needed the point on the y-axis. Any questions on that? No? Got it? Good. All right. So we're starting something. So I want to talk about exponents today. So we're going to introduce exponents, and we've seen exponents already. We're just going to put them in a more pretty outlook, I guess. No, just whatever powers I can dream of at this point. But anyways, the exponential notation, a to the power n, we call a is the base, and n is the exponent. And for now, we're going to let n be a natural number, meaning it's a positive integer, so it's a whole number. And the way this works, a to the power n literally means a times a times a times a, total of n times. Is that okay? Did you learn anything new? No. Good. You shouldn't have. So if I write something like 3 to the power 4, you all understand what I'm talking about, right? What does that mean? 3 to the power 4, what does that equal to? 3, 3, 3, 3, so you'll get 81. But yes, it is 3 times 3 times 3 times 3. 4 times. Bless you. You all happy with that? Okay. Okay, so I just want to jump in and talk about rules of exponents, because we're going to be doing a lot of that. We'll be multiplying, dividing terms that have similar bases but different exponents, and raising things to power. So we're going to start listing our rules of exponents, and there are going to be about 10 of them total. We might not get through all of them in this semester, but we'll get a few out of the way. Okay? So rules of exponents. So let A and B be real numbers. And let M and N be natural numbers. So the first rule when we multiply two exponential expressions that have the same base. Okay? So yes, you just said add exponents, so good, but why? What? I'm sorry, I didn't hear you. Well, that's not the reason. I mean, they'll be redundant to put it inside the circle, but it's not the issue here. So why do you think we're going to be adding them? For example, if I have 3 to the power 5 times 3 to the power 4 would be probably better. Okay? So the suggestion was, well, that is the same as 3 to the power 5 plus 4 equals 3 to the power 9. So we add exponents. I want you to convince me that that's what you have to do. Why do you think that rule is there? Why do we add exponents? I'm not sure what you're trying to say. No, it'll be the same thing. But if I go along with what you're saying, if I actually look at them separately, 3 to the power 5 is that, right? Times 3 to the power 4 is that, right? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 3's multiplied together. So we add exponents. So the rule is we add exponents. So when we have the same base, we add exponents. And this is one of the reasons, because we can just using the definition. If you write it all out in all the terms, you're going to have precisely m plus n total of those things. So then when we divide, if I take a to the power m and I divide it by a to the power n, we will be subtracting exponents to get the actual answer. Okay, for example, if I do something like this, 3 to the power 6 divided by, I don't know why I'm picking on 3 today, by 3 to the power 4, this rule tells me to just, well, that's the same as 3 to the power 6 minus 4, which is 3 squared. We just subtract exponents. And the reason for it, if I write this as a fraction, if I write it as 3 to the power 6 over 3 to the power 4, what that means is 3 times 3 times 3 times 3 times 3 times 3, total of 6 of those in the numerator, and then 4 in the denominator, right? Then I can just do that. I can cancel out the pairs of 3. And then I'm left with just 2, 3 squared. So this is why this rule works. Of course, you're not going to be writing it out like that. You're just going to go one exponent minus another exponent. But it's kind of the reason why that works. Okay? Is that okay? The third rule is when we take an expression that has a power and then we raise it to a power. So a to the power n raised to the power m Who knows? What do we do with exponents here? Multiply m times n. Okay? And again, one way to see that, let's say if I have x cubed squared. Okay? According to this rule, it's going to be what? X to the 6. That's right. We're just going to multiply 3 and a 2 to get x to the 6. But the reason why that works, if I write it all out, x cubed is x times x times x squared, like that. And square means multiply by itself. So this is x times x times x times itself, x times x times x. So total of 6. Right? Okay, so these are the reasons why we multiply in this case. So we have 1, 2, 3. Now the fourth rule, if you have a product of two numbers and you raise that product to a power, that is the same as raising each of those factors to that power. So a power of a product is product of powers. That's really what it says. So we can kind of distribute those exponents only with the product. If there was a plus in between, we cannot do that with a plus, only with the product. So again, the reason why that works, let's say if I have AB, I don't know, to the power of 4. Okay? Yeah, you don't need to write that down, but it's really, power of 4 means AB times AB times AB times AB 4 times, right? That's what AB to the power of 4 is. Well, it's just a product, I can rearrange that product anywhere I like, so I can actually write it as 4a's followed by 4b's, which is a to the 4th, b to the 4th. No, AB is a times b, that's 2. But again, those are just little, those are not official proofs, they're just little ways to see why those rules apply. Of course, you're not going to be writing that out. You're just going to say, well, it's a to the 4th, b to the 4th. And the same thing goes for the division. If I have a over b, so that's rule number 5, a over b to the power n, this is the same as a to the power n, b to the power n, like that. Is that okay? All right. I'm going to give you the 6th rule. That will be the last one for today. Do you know what happens when you take a number and raise it to the power 0? Turns into 1. That's right, provided that a itself is not 0. If you take your calculator and you think of any number that you like, what's your favorite number of today? 5. If you take 5 and you raise it to the power 0, you will get 1 every time. As long as it's not 0, as long as the base is not 0 itself. Look what happens if I go 0 to the power 0. Oh, that's full of crap. This thing is broken. 0 to the power 0 equals, this thing is broken. Oh my God, that's broken. You just completely ruined my moment. Wow. No, it's just you gotta write them. That's why Microsoft is in trouble. Their calculators are broken. Wow, this is just, oh my God, never noticed that. Does anybody have a calculator? Yeah, punch it on your calculator with 0 to the power 0. That's completely to the power 0. Type it on your calculator. On your calculator, you have this little kind of a hat caret sign. Yeah, quit, because, yeah, it's about, right, it's error. It's undefined. 0 to the power 0 is undefined. What is that? No. That's. By the way, for the we're about to have a test, right? It's okay to bring a calculator to the test, but it cannot be a phone, iPhone, iPad, iPod type of calculator. Basically, you shouldn't be able to get online with your calculator. That's the whole message. It has to be a designated calculator. I know with the new calculators, but then, if you figure out how to work that thing, then you probably don't. What? Anyways, anything to the power of 0 except for 0 equals 1, always. Except for 0. Can I do 0 to the power of 0? That's undefined. Okay? That calculator made me upset. Why is it doing that? It's not supposed to be doing that. Am I even typing it right? I think it's not even allowing me to do that. See, if I go 5 to the power 0. No, it's stupid calculator. Now, why is that true? Why is that? How does it work? Now, don't write anything down. I'm just going to work it backwards. Just pretend we're looking at, 5 to the power 0, right? 5 to the power 0. So that 5 was our favorite number of the day. Do you have another favorite number of the day? 7. Do you agree that 5 to the power 0 is the same as saying 5 to the power 7 minus 7? Right? It's still 0 in the numerator. You agree with that? Now let me ask you this. Have you seen today an instant when we subtract exponents? Yeah, when do we subtract exponents? Division. So based on rule number 2 on this list, subtracting exponents is equivalent to dividing, so that means it is 5 to the power 7 over 5 to the power 7, right? Which is 1, because your numerator and denominator are identical. So then you get 1. And you see how 5 and 7 were totally random? So it doesn't matter what those numbers are. But if you put 0 in there, if you put 0 like that, and you write 0 to the power 7 minus 7, so it's 0 to the 7 over 0 to the 7, that means you are dividing by 0. And that's undefined, right? So it's still undefined. I'm just curious. If that calculator going to tell me that 0 divided by 0 is 1, then I don't know what. 0 divided by 0. All right. Okay. So now that's undefined. Oh, you stupid calculator. See, I would have some respect for it because if this was consistent. But it's inconsistent and it's wrong. But it's right about the division. So undefined. So this is why 0 to the power 0 is undefined. It's a weird thing. 0 to any power is 0, and any power of 0 is 1. But you put them together, it explodes. Right? Because if I ask you what is 0 to the power 7, well, that's 0. No problem, right? It's 0 times 0 times 0 7 times. That's 0. Okay, good. So let's do some examples. What? No. Well. Okay, how about we'll take x to the power 3 times x to the power 4. What does that equal to? X to the power 7. Very good. Are we all happy with that? How about AB to the power 6 times AB to the power 4? What does that equal to? Right. And AB should still have parentheses around. Because if you don't put parentheses around AB, that means only B is raised to the power 10, but not A. Okay. How about x plus y to the power 7 divided by x plus y to the power 2? What does that equal to? X plus y to the power 5, because we want to subtract exponents. As long as the bases are the same, and I can make my base anything I like. So what it looks like, a summation of some other items, it is still going to be x plus y to the power 5. Is that okay? What if I do this? If I start with a smiley face, and it is cubed, and then raised to the, I don't know, I'm going nuts here, star power. So smiley face cubed, and then everything raised to the power of star. What is that going to give you? So smiley face, so the base stays the same. 3 star, excellent. So you get my point? So those things don't really matter. So yes, 3 star. Oh, believe me. Yes. Smiley face. Let me ask you this question. How about x to the power 5 times x to the power star equals x to the power 20. Can you tell me what star is? Star is 15. Very good. Because you know we're going to be adding exponents. So you're actually building an equation. You hear that? You're actually coming up with an equation that says 5 plus the star, come on star, show up, equals 20. See what he's doing? He knows that you have to add exponents on the left and to get 20 on the right. So then you solve for the star. So the star, come on star. Okay, so star equals 15. Does that make sense? How about this one? Star to the power 3 equals xy to the power 12. Can you tell me what star is? So xy. So what the star have to be, so when you cube it, you get xy to the power 12. Xy to the 4th. Does that make sense? Well, ask me questions. Good. That's why I'm using them. You're about to hit a worksheet, but the star just takes place of something. It's just something. You want me to replace stars with smiley faces? It's going to work out better? Is that what you're saying? I will. Don't worry about it. We're getting into the abstract algebra now. So yeah, we'll use stars and smiley faces. What? Now, do you understand where he came from with that? He said you had something that you're cubing, and you're getting xy to the power 12. So first of all, you realize when you raise power to power, you multiply powers. So you're asking, okay, well, what power? So what times 3 equals 12? So that's where 4 comes from. Yeah, so that's what star is, right? The star is inside the parentheses. So if I replace star with that expression, it will have the cubic on the outside, like that, right? So yes, you're right. The star is inside the parentheses, so all that will go inside the parentheses. Does that make sense? Good. Sounds fun. Okay, how about this problem? 17 cubed times 17 to the power 4 divided by 17 squared all over 17 squared. Can we compute that expression? All right, well, you're just giving you way ahead of me right now. Tell me what you're doing. Okay, so very good. So first of all, you realize that you shouldn't be pulling out your calculator and typing in 17 cubed in it and 17 to the power 4 and all that, right? You don't want that. Did I tell you that every time you feel like you need a calculator, you most likely don't? There's another way of doing that. But yes, we realize that the product means we have to add exponents. So you get 17 to the power 7, and then 17 squared here, And what did you do in the denominator? So 17 to the power 4. Is that okay? I'm just taking it very slowly. But yes, I will subtract 7 minus 2 to get 17 to the power 5 over 17 to the power 4. So yeah, we're still subtracting. So it's 17 to the power 1, which is still 7. So all that ugly mess was just 17. Does that make sense? Mm-hmm. Yeah, so because I have a division here, so I went 7 minus 2 to get 5. Yeah. Very good question, yes? I'm not going to talk about it yet, but yes. Right, because you're absolutely right. This is the danger of what we're doing, because when you start subtracting things, there's a potential to get negative answers, right? So you're absolutely right. If I had something like this, for example, if I had 3 to the power 7 over 3 to the power 9, okay? If I have to subtract exponents. So then it's 3 to the power 7 minus 9, which is 3 to the power negative 2. Okay? So here we go. Now, right? I didn't do anything wrong. I got a negative exponent. So there is such thing as negative exponent. Do you know what that means if you have a negative exponent? Anyone? Have you seen negative exponent before? Roots of fractional exponents. But if you plug it in your calculator, I have to be careful now with this calculator, but it will give me a nice answer. Because look, if I go 3 to the power, and I have to be very careful to make sure the entire negative 2 is a power, so I'm going to use parentheses, and then negative 2, close parentheses. You know what the answer is going to be? 9? No, it's going to be 0. It's going to be decimal, like 0, 1, 1, 1, 1, 1, 1, 1, 1, like that. Very good question. Why? Now, let's look at that. Let's try a different approach. Do you know how to reduce this to? Can I reduce this fraction? Because look, don't write this down, but I can think of 3 to the power 9 is 3 to the power 7 times 3 squared. Do you agree with that? That my denominator is still 3 to the power 9? So now my numerator and denominator have a common factor. So I can cross out 3 to the power 7. Is that right? So what's left in the numerator? 1, because we divided, so we're left with 1. Denominator is 3 squared, which is 9. So it's 1 over 9, right? And if I actually plug in 1 divided by 9 in my calculator, I'll get the same thing. So the negative exponents are reciprocals. So 3 to the power negative 2 is the same as 1 over 3 squared. So every time you see a negative exponent, that means that goes in the denominator. You don't need to know that in Math 090, by the way. I was just answering a question. Okay, that's a very good question, because we subtract exponent, we potentially get into negatives. When we're multiplying exponents, we potentially can get into fractions. So we can get into fractional exponents. So that also exists. We can do things like, hey, what is, what would be a good number? 9. Don't write this down, but I can do that, like 9 to the power, let's say 3/2. That makes mathematical sense. We can figure out what 9 to the power 3/2 is. And actually, if you use a calculator properly, the answer will come out to be 27. Try it on your calculator. If you take 9 to the power 3/2, Make sure you put parentheses around 3/2. Otherwise, your calculator will raise 9 to the power 3, and then it will divide everything by 2. Your calculator is you have to be, over parenthesize everything. Yeah, when in doubt, put parentheses. Because your calculator is not, depending on the calculator, it might not be aware of order of operations. It might be that bad. Did you get 27? Okay. So on this calculator, if I go 9 to the power, and I'll use parentheses, 3/2, so 1.5, I'll get 27. Okay. So there are ways to do fractional exponents. Again, not in this class. We'll do fractional exponents in 099, but not here. So anyways, I was just answering a question. So no negative exponents yet, no fractional exponents yet. Because those will give us 4 extra rules. I told you we're going to have 10. So far, we'll only have 6. Right? So 6 rules so far. So any questions on that? Isn't that fun? Rules of exponents? What? Okay, good. I'm glad you like that. All right, good. We'll just introduce that. Now we're going to